Okay, let's get started. Pass that around. We're doing 19 and 20 today, which is design and cladding systems. I hope you read it. Then we'll do 21 on Wednesday. Then we will have a test on 17 through 21 next week, probably on Monday. And then we do our last 3 chapters in our final project. Almost over. So, hope you're working on your final project, because remember, a draft of that is due actually next week. I need to see evidence of your working on the final project. Either a draft drawing, a draft paper, something like that, okay? So today, like I said, it's 19 through 21. Let's see if that works. Yep. Talking about the cladding. Cladding for buildings is the outer skin, like a curtain wall it can be. The purpose of it is to keep the water out, to prevent entry of rain or snow or ice into the building. There's a lot of forces that would draw water into a building that you'll see in this chapter. We'll look at that. And actually, the taller a building gets, the more acutely the water is driven into the building. You also need to prevent air leakage, because obviously you don't want the cold or the hot air. Just set it there in case others come in. Cold or the hot air to come inside or outside, whichever way you're trying to do it. So you have to prevent air leakage. You need to create a pressurized building so that the windows won't blow out. This is especially true in skyscrapers, where, as the higher you get, the colder and windier it is, just like in a plane. So, and a lot of times, in these very big buildings like the Burj Dubai or the World Trade Center, stuff like that, it's a whole different climate when you get to the top floors, and it has to be designed differently. It may look the same, but there's different factors involved. Cladding also controls light, because it'll be windows. You want to have natural lighting in your spaces as much as possible. But you also need to control the heat radiation in that, because before we had all these specialized windows with mirrorized films and powder coatings and stuff, the heat would just literally make the skyscraper a oven. So your cladding has to control both the light and the heat. Conduction of heat, remember, is when heat travels through something, like a spoon on the stove is in your hot soup, heat travels up to the handle. That's conduction. So it needs to control that. You need to have a barrier, some sort of, usually a rubber synthetic material that will stop that conduction going from the outside to the inside. It needs to have insulation. The thermal bridge is a part of conduction. That's where you might have, a piece of metal that actually spans the distance. That's a thermal bridge. So you want to eliminate that. It also needs to control sound. You don't want to, if you're in a quiet office, you don't want to hear the sirens and all the messy traffic down below. So insulation helps to control the sound. So this cladding they're showing on this picture has optical properties and external hanging shades, it looks like. Controls the passage of light and heat into and out of the building. It has mechanical things that they can control, depending on where the sun is in that part of the day. Secondary functions of cladding. Resisting the wind forces, provide adequate strength and stiffness to sustain the pressures and the suctions due to the wind. As you get higher up in the building, like I said, the pressure is much greater, and you have to really strengthen your cladding to withstand those pressures. Water vapor, you don't want water getting in there for obvious reasons. Water is the devil in construction, so you need to keep it out at all cost, or else it'll destroy your building. This is just a little slide on, hold on a second, what's this green thing? Hold on. I don't know if it's showing my, because I'm recording this. I want to make sure it shows the whole thing. That's not sure what that green thing is. Hold on one second. No. Resume. Okay, anyway, sorry about that. So thermal expansion and contraction. When it's cold, things tend to shrink up. When it's hot, they swell up. So your cladding has to be able to accommodate movements in the structure from expansion and contraction, both from thermal and moisture. You know, moisture can make wood swell, or a lot of products swell up, and then when it goes away, it makes it shrink up. So your cladding has to control that as well. Movements, there's always going to be movement in a building, so there has to be enough give and take in your cladding so that the pieces can move within it without cracking or destroying the structure of the building. And that's just a little slide on how things can move or slide or adjust. And it's just something that happens. Nothing is ever still, even though it may appear still. Needs to resist fire for obvious reasons, unless it's a building where they train firefighters. So it has to have fire properties, and that'll be all called out in the standards and the specifications. It'll have to meet certain fire resistant properties. Needs to weather gracefully, excuse me. There's a sign-in sheet here for those of you that just came in. Needs to weather gracefully, shouldn't collect grime and dirt. You should be able to clean it, or it should just, the dirt and stuff should fall off of it easily in the rain so that it washes itself. It should not oxidate, and it shouldn't, fade. The color shouldn't fade. And, you can tell newer buildings are much better than that than older buildings, just because the science gets better. So, and they can make materials that won't fade or look old before their time. So when you install it, you need to obviously, especially on the tall buildings, you need to watch out for your installers. You notice that these guys are all harnessed in. They're buckled to a rope that's, if they happen to fall over, they won't go too far. It's kind of like mountain climbing, if you've ever done that, or cliff climbing. You're all harnessed in usually. Usually, some people don't. But you also need to have tolerance, because these panels here are prefabricated, and so there needs to be some wiggle room when they get that up there, because they can't just take it down and rebuild it. There has to be some little wiggle room in case something's a little bigger or smaller, or they didn't pour that column right in the right spot. And they usually accomplish that with some enough space in their joints, and then they'll fill the joints up with some filler or some caulk or stuff like that. Levels of redundancy, the air barriers and the drainage channels, to get rid of moisture from faulty joints. You have to do 2 or 3 levels of that to make sure that there's no way that the water especially can penetrate your building. You need, like it says, generous edge clearance for your glass so that it won't hit any hard surfaces and crack. So how do you make your cladding watertight? And it's going to talk about some conceptual approaches. So water will find a way in if you allow it. It can be kept away with overhangs. That's a big factor, especially that's why we have overhangs usually on our houses and small commercial buildings. It can be sealed with sealants and gaskets, but there is a force. The force is always present. It can be neutralized at a plane on which the outside, on the outside of the weather barrier. So here they're just showing you that the water will drip down, and if there's an opening here, it'll find its way in, because this is positive pressure and negative pressure, and the water will be drawn in if it can get in there in any way. So when you have breaks in your finish, this is obviously the wrong way because what does the water do? It falls down and, oh, look, it just easily rolls downhill and inside. This one is the correct way because it falls down and it usually won't try to roll uphill. So that you want your cuts to be beveled toward the outside. Whenever you're building something, think of how the water's draining. Just like when we studied roofing materials, you layer it from the bottom and up so the water just goes down the bottom or never has a chance to go uphill. Momentum forces is a consideration, showing here in this picture where the droplets will come and they'll bounce in. So to fix that, you have this like, what do you call it? Labyrinth, where the water bounces here, it bounces there, bounces back, bounces back. It's very hard for it to bounce all the way up into here. So that's a better way, is to create a labyrinth. Tension is where the water runs across the surface, and it'll stick to the surface until it can't stick no more. So you got the water running down here, and then it'll just sort of ooze over this way, and then it'll fall down and go down that way. If you make this little drip, or is that the right word? Yeah, drip. The water comes here, there, and up. It can't really go up, so it's going to go ahead and fall down, and then go. And then this is slanted out, and it'll go down. Capillary action is where the tension effect that pulls the water through an opening can be bridged by a water drop. So this is the wrong way because that can just fill with water and it can go down. This is the right way because that's bigger than the water drop, so the water drop stops there. Although I think this wouldn't be the ultimate solution because it could still squeeze on over that way, but it's better than this side. Then you can also make a pressure equalization chamber, which we'll see in some details specifically in a little bit. So you got your outdoor positive pressure and your indoor negative pressure. So this is a little chamber that equalizes the pressure so that the water won't just flow into there. It'll hit this pressurization chamber and it will just fall straight down. And that's especially important, in the taller buildings. Rain screen cladding and pressure equalized wall design. So you allow the wind pressure differences to neutralize with your pressure equalization chamber. This involves creation of an air barrier plane of air tightness. An air barrier is protected by rain screen, which is an unsealed labyrinth joint layer. This is the labyrinth. Pressure equalization chamber, which is the PEC, is between the rain screen and the air barrier. The PEC must be divided into compartments to prevent cross currents. The rain screen cladding is used to describe systems that have internal drainage regardless of the level of compartmentalization and the degree or pressure equalization. So it's a lot of scientific stuff for these two panels coming together, but all of that is, in these simple little details, that's how they can keep your inside dry. Here's an example of a metal panel pressure equalized wall. You can see that no surface joint sealants or gaskets are used. The metal rain screen panels do not touch each other. See, right here. So there's no way that the water can just keep going. The gaps preclude capillary movement. That's because they don't touch each other. The labyrinth joints are created. You can see that. The sloping surfaces counteract the surface tension, so it's sloped downward. The installation is simple and forgiving, meaning you don't have to have a master of rocket science to do it. The space between the metal rain screen and the insulation provides a drainage space. And the pressure equalization chamber, which is the PEC, is divided into narrow compartments by vertical and horizontal channels. So this is also true in our simple home design or residential with your window. You have a lot of those same elements. The weather stripping acts as an air barrier, keeping the wind pressure out. There's the weather stripping right there. And if you look on your windows at home, you'll see this stuff or something similar to it. The open joint under the sash rail is provided with a capillary break and acts as a pressure equalization chamber. So that's right here. The wash or the slope of the sill acts to facilitate drainage. It's sloped outward. The groove at the edge of the sash acts as a drip right here. So the water comes down here and it won't go up past there. It'll just drip on down to the ground. And the L-shaped joint between the sash and the sill acts as a labyrinth. So the L-shaped joint right here, I guess, is what they're talking about. So you can see a lot of the same elements in a simple window, residential window application. So sealant joints and cladding, that's something that you have to do right, or you might as well not do it at all. So, and a lot of, that's something that does require someone that's trained in it. So most sealants are gunnable. You've probably all seen caulk guns before. And it's a sticky material that's injected into the joint, and then it sort of expands or, fills in the area. There's 3 categories. There's low range called caulks with low range elongation used to fill minor cracks, meaning they don't swell up or get very big. Medium range, such as butyl rubber or acrylics, are used for sealing non-working joints. So if the joint's not going to move, they'll use that because it's not as, doesn't expand and contract as much. And then high range, such as polysulfides, polyurethanes, and silicones, are highly resilient and durable for 20 years or more and used for working joints. So if a joint's going to move around, expand and contract, they'll put that in there because it will stick with it and stick to the edges. Gaskets are strips of elastomeric material. They're compressed into the joint or installed using a lock strip insert. They seal up the joint once they're installed. There's also preformed cellular tapes and preformed solid tapes that will seal joints as well. And these are just showing you pictures of those. And this is how to seal your joint correctly. And tooling is important. You can't just squirt the caulk in there and leave. You got to tool it when you're done. Just like on the brick and the mortar, you got to tool the joints. So you have to have enough width to control the strain, depth to control the stress, and the correct proportioning to control the strain and the stress. So there's typical steps. The joint must be cleaned of oil, meaning you got to get all the foreign debris and try to make it as clean as possible so the stuff will stick. And then you apply a primer. A backer rod is this piece right here, which is, I think it's like a piece of foam they just stuff in there in the back of the joint. And then the sealant is extruded onto the joint and tooled. If you don't put the backer rod in there, obviously you might just squirt into oblivion. So that's why that's there. So this is what it looks like untooled. This is a section cut through it, and this one's tooled. They've obviously run their tool down and made sure it evens out. This one, the joint is too narrow. Joint too narrow. That one looks like it's too wide. Or maybe, I'm not sure what they're trying to say there. Or maybe it expanded and then it pulled apart. Because you have to have the proportions correctly. Here the sealant bead is too deep. The sealant bead here is correctly proportioned. It will expand and contract. And a lap joint correctly proportioned. Sealant joint design bond breaker. Sealant joints should only contact 2 sides is what they're saying here. If it contacts the 3rd side, it will break the bond. So they'll use a bond breaker, or it'll break the sealant. They'll use a bond breaker material to prevent it from coming in contact. So here they've put the bond breaker so that when these move and expand and contract, that will act like it's supposed to and not just be stuck to this side causing this breakage like it shows there. Temperature, you need to take into account all the seasons when you're specifying your joint sealers and what your, how will it react in the summer, how will it react in the winter. Make sure that it, can handle the wide range of temperatures and weather conditions, and specify one that will. So the basic concepts of cladding systems. Load bearing and curtain wall. Load bearing, until the late 19th century, large buildings were built with load-bearing walls. Really stone walls going, or masonry, so they couldn't make them very tall, because if you did that, then you would have to have such thick bottom walls that it's hardly worth it. So it probably limited them to 4 or 5 stories in reality. Plus, you didn't have elevators, so you didn't want to walk up that many flights anyway. So all the buildings were load-bearing. Everything had a structural intent. They weren't very good insulators. They developed water leaks, required larger foundations, obviously, to hold the weight of the walls. And so modern-day load-bearing walls have been brought up to date with a higher strength masonry and concrete with components such as steel reinforcing that reduces. Steel can hold a lot more with less weight. Insulation cavities, flashing, air barriers, vapor retarders. And then now we have the curtain wall. This was introduced in the late 19th century with the advent of skyscrapers, like I said. It is the exterior wall supported at each story by a frame derived from an idea that the wall is thin and hangs like a curtain. So you have your structure, that's all your rigid, and then your little curtain pieces hanging on it. And that's your exterior cladding. The cladding has no vertical load. Its only job is to keep the wind and the rain out and hold on tight to the wall. But it doesn't support the building at all. If it was to fall off, the building would still be there. You can have curtain walls that are actually made of stone and masonry, which we'll see. You may think that, you go downtown and you see this granite, but it's really only that thick. It's hanging on a framework. But it appears monumental because of its stone. Testing and codes. Of course, all the systems have to be tested, make sure they meet code, especially in areas, on the Gulf Coast, like Houston. They have to make sure those buildings, the cladding doesn't just fly off in a windstorm. In here in Corpus, too, especially. So you have tests for resistance to air infiltration and water, structural performance, and thermal properties. Sometimes full-scale tests with a 2-story high specimen will be conducted in a laboratory to make sure that it meets the standards. And again, we have the American Society for Testing of Materials, which is the one that most people use for testing. And then a lot of times they'll do a mock-up in the field too, if it's that important. Let's see. This, I think, is just, sort of a video that shows the process of putting a wall on, which I'll show you, but there's no words. It's kind of like puts you to sleep, but you may or may not like that. The major impact of the building codes on the design of the exterior wall is the structural strength, the fire resistance, and the energy efficiency. Structural strength and stiffness of the wall and adequacy of attachment. It has to be attached so it doesn't, the attachment has to be strong. Fire, they measure combustibility, fire resistance rating, and fire stopping. And energy is the thermal resistance. This is especially important now with the energy conservation and all that. They want to make sure that, that you have a thermally tight envelope. So I think this is the one that probably enough of that. Let's see. Okay. So then it moves into chapter 20, which talks about the masonry, veneer curtain walls, and I think some stone as well. Or maybe that's 21. I can't remember. It all runs together after so many years. So what do you do for a masonry? Like this building is a masonry veneer. I don't think the masonry on the outside of this building holds anything up except itself. It's built just pretty much like this on a structural system. There's columns, and then there'll be these angles that the masonry will sit on, and probably for each story, it just supports itself. Like there'll be a ledge at each story. There'll be a soft or horizontal expansion joint, which you can see if you look closely. Probably you'll see a slightly different color if you go outside and look at it. The flashing is tucked into the backup wall, so you don't really notice that either. Here you can see how it's kind of built up. This is your flashing that comes down, and then your masonry is on top of that. There's your weep holes that we've talked about before. And then they'll have a glazing system wherever that needs to start. Here's a good detail for you to study, perhaps copy for extra credit, of a masonry veneer system. So you got this is your structure behind that is obviously a concrete floor, and there's a concrete beam. Then you got some concrete blocks. I don't know if any of you are actually doing masonry cladding for your project, but this is a good example. So you've got that. Then you've got your 2 inches of insulation on that side. Then you have an air gap, and then you have your brick. So here at each floor, you're going to have this angle right here, this metal angle that's bolted in to your structure. And you'll also have flashing that comes out over that insulation there and there. You'll have caulking right here. Then you'll have your bricks going on up to the next floor. These are the metal ties that are every so often to hold the brick back to that so it doesn't just fly off. Here's a picture of the metal angle, how that might be attached. Here's another way it could be done with, if you had, instead of concrete, if you had steel beams and girders. So that's something you might want to go back and study. Just make sure you understand all the terminology there and everything they're talking about. And this is also when you draw your final project. I mean, I know a lot of you are beginners, but see how nice and straight the writing is. It's architectural, if you're doing it by hand especially. And there's leaders, and so this is a good example of what your hand drawing should try to emulate. And if you need tips on that, I'll be glad to help you. That's what the draft is for, so I can help you. Don't just throw you out into the deep end. So here is vertical joints in masonry walls are also needed to control the movement, and they're showing you some here. You can see them right there, and you usually put them, if the architect will decide where those go so they look nice and don't just look like they're thrown up there some way. Here's another good detail of a brick veneer with a steel stud backup. And if you look at that, here you've got your steel that's been fireproofed. It's got a fireproofing coating on it. You got your trusses. You got a concrete deck for your floor. And then you're going to have, let's see, here's the angles coming down. It's attached to this steel strut. Then this ledge angle is right there. And then your brick piles up to the next floor. You've also got, if you looked closer, you would see the flashing and all of that stuff. This is just regular batt insulation, it looks like, behind the sheetrock. And then another layer of sheathing to provide strength for that, and then there's an air gap. Here you can also prefab your masonry. It can be brought to the site just like in that movie, and they can just hoist it into place. And there's a lot more control, obviously, in the factory if you can build it there. If you've got a repetitive form that can be used over and over and over again, that's a good way to do it. There you can see them putting a corner piece on that, what looks like a parking garage, perhaps, and then a flat piece as well. Stone curtain walls. I knew it was here. So stone, much like glass or brick, you have a backup structure. You can see in this picture, you got the concrete columns, and then you got a grid system that's attached to your structure, and then your stone panels snap into this grid system. And then you can also have window panel, glazing panels, and then so it appears very monolithic and heavy, but in reality, it's probably heavier than if it was just glass, but it's not too heavy for that structure. Here you can see they've wrapped the structure. They've attached these steel clips that the stone will snap into, and there's there's either bolts or grooves, and it forms a pattern of stonework. But anyway, so you can see better how that's done. Here's one of those clips that goes into a groove that's in the stone, so that once it's there, really, and then the next stone piece will go on top. It won't go anywhere once it's there. Here's a building that is a stone cladding, and with a steel structure similar to the one we just saw with brick, but now they're going to use a stone system. Notice the drip edge even on the stone so that the water doesn't creep in there. And then here, the stone is pre-cut so that it'll snap into this for this particular system. This is the roof detail, because you'll have the stone will stick up past the roof, then you'll have this roofing material that's canted down and all this flashing so the water doesn't get down in there. Here you can see how they would strengthen, you have to strengthen if it's a thin piece of stone, so you'll put some steel stuff on the back of it just to make sure it's stiff and doesn't, buckle or break, because it has to be designed to the wind loads, and they hoist it into place, just like we saw in that movie right there. You can also post-tension limestone and spandrel panels. So you got thick blocks of limestones, maybe filled with adhesive. So these are all separate blocks, and they're filled with adhesive, and then there's a cable or steel that goes through there. They pull it tight just like with concrete, then they let it go, and it all contracts back. And that makes a very strong panel. So for thin stone facings, like I said, they can be strengthened with structural backing, such as metal or honeycomb. Very thin sheets may be used as facings for precast concrete. So you might have concrete stuck to the back of it, actually. You need to obviously work closely with the stone manufacturer. They know the properties of the stone. Limestone is very brittle, so you can only cut it so thin before it's pretty worthless. So you need to, if you're going to do something like that, you work closely with the manufacturer or the mason. So precast concrete is another cladding system you can obviously make it in a factory where you can do highly repetitive forms and then hoist it up into place. You can have lots of different finishes on it, so it looks like stone. It may look like wood. It may look like, they have that pea gravel look where it has all the little round rocks. You can strike it to make it look like bricks. So just pretty endless what you can do. Or you can even inlay bricks into it. And of course, here's the precast. They're making it in the factory here, a sandwich panel that will have insulation. It'll have a ribbed finish, you can see here. And then it'll be very thermally tight and economical. Here's a detail of that. This one is, you got a concrete structure there. You've got your angle that will hold this piece of precast concrete. Then you have your labyrinth. Remember we were talking about that. The drip edge, the sealant. There's some interior sealant there. So that's another good detail to copy and study. Here's a building where they're doing the installation of some precast concrete cladding panels. You can see how it works pretty efficiently. Here's a good side view. You can see the insulation right there. You can see the fire stopping, or I think that's what that is, the slightly darker colored band insulation at the slab level. Yeah, that's safing or fire stopping. And you have to do that between the levels of the floor, because like if you're down here on this floor and a fire breaks out, you know, the smoke will travel wherever there's a hole. So you have to seal up between the floors with this, or any openings with this fire safing, so that, you know, you can confine the fire to the space that it's in, and it reduces the chances of it spreading. Here they're talking about glass fiber reinforced concrete curtain walls, GFRC, which is a pretty new lightweight cladding material. Obviously you can mold it into shapes and have a little bit more freedom with your design. Here's a detail of, you know, cutting through the wall of one of those and how they've made the shapes. I've never actually used this stuff or seen it, so, except on boats. I think that's what they make boats out of. But so, steel rod anchors can flex to accommodate the small amounts of movements. That's what they're talking about here, so that the building can breathe and move and it won't destroy the panels. Here's how they would treat the joints. Still, you've got their backer rod and you got your sealant. This is a parapet. Parapet is a wall that sticks up past the roof. So you cover that with your cap. You seal it. You caulk that so the water will fall off into the roof and down the drain. Here's another different kind of parapet detail. It all depends on the look you want. So exterior insulation and finish systems. Hi.
I'm going to be going home sick.
Oh, okay.
I'm going to put the degree plan deal in your office if you want to advise the registrar.
Oh, that's right. They registered today. Oh, they registered today.
Yeah. I plan on doing everybody's registration advising Tuesdays and Thursdays from like noon to 3:30, just if they want to wait.
Okay.
Whatever, but I'll put it in yours just in case anybody needs it today.
Okay. Hope you feel better. All right. Where was it? So EFIS. EFIS has become a dirty word to some people, because if you look at, if it's installed wrong, it's a disaster. So it's a good material, but you have to install it as specified, meaning that it has to have the proper drainage and air barriers and all that stuff, or it'll just turn to a moldy mess. It stands for exterior insulation and finish systems. It's basically insulation with a thin layer of stucco on it. So if you see commercial buildings that appear stucco, it's probably this EFIS system. In commercial construction in general, they can afford the contractors to hire the skilled, trained labor for that kind of stuff. When you get into residential construction, usually they don't. So like out on the island, there's a few homes that were made of this EFIS and not done correctly. They don't have the air barriers and all that stuff, and they just look like a pile of mildew. It's gross. But so you just got to be careful. Like, as with any product, you're supposed to do it according to the manufacturer's specifications. They write them for a reason, and they won't guarantee it if you don't do it that way. So you can put this product over steel and masonry. Here you can see a panel going down there. It's very good for this kind of a commercial, multi-story construction, but I wouldn't do it on a house. Here's a close-up look. It has a drainage mat, the insulation, and then the thin layer of a stucco type material on the outside. So what's going to happen in the future? So rain screen. Most masonry and concrete cladding systems except brick veneer are barrier systems. And there is really not a well-organized system of drainage, because brick has the weep holes, so there's a well-organized system of drainage. So you need to make sure that you think about how it's going to drain if the water gets in there, because it will get in there. There's just not a 100% way of keeping it out. So the cavities behind these systems that are when they get interrupted by the framing and attachment components, that's where you've got to worry about it. So you need to provide some sort of drainage mechanism when you do that. And you can see here on this stone one, they've got the drip edge and they got the labyrinth, and hopefully there's some sort of sealant that comes down like that. So, you know, they're doing their best, but it's stuff that you have to, you want to screen against the rain. So cladding is found in these sections of the specifications, and precast concrete is in 3, and masonry is in 4. Stone is in 4, because that stone and masonry are considered the same or similar. Thermal protection, which would be the insulation properties, is found in section 7. So this is a detail I wanted to kind of work on together. Let me see if I can get this set up with the, so I can draw on it. I never can quite figure it out. Hold on. Un momento.